Welcome back to ECE 207. Hopefully I'm in the right place, and so are you after almost a month of class. 3 weeks, is that true? 7th lecture. If you're watching them, you have my sympathy. No. Hopefully if you do miss something in class, you can take advantage of those videos if you want to replay it a few times to see if it makes sense. Today, what I want to make clear is homework or exam number 1 is a week from today. Homework 2 is due on Thursday. And hopefully we'll cover the material that will help you with those last 2 problems, and in particular Thevenin and Norton equivalents. We'll talk about that today. And we will discuss the Wheatstone bridge before getting into new material, Chapter 3, which will not be on exam number 1 this time. Even though on the practice exam it may show some problems from Chapter 3, we'll just create some other problems from Chapters 1 and 2 for exam number 1. Question? Thursday, I don't know if I'm going to go over any kind of a review. I feel like I'm behind, so I may just keep going with Chapter 3 material. I have to decide what I want to do with respect to getting you ready for the exam. I may create another little video and have you watch that for preparation for exam number 3 in terms of what to expect. But really, homeworks 1 and 2 are the material that will be covered on exam number 1. And if you can do the homeworks, if you can do the practice exam, hopefully you'll be in good shape for exam number 1. That's the idea. Let's then get started. Question?
Is it completely closed note, or are we allowed to do one?
Oh, I knew you were going to ask me. I haven't decided. I'll try to let you know on Thursday. It's mostly closed book. I might provide you or allow you to create one sheet of notes or something. And that sheet would obviously be constrained to 8.5 inches by 11 inches. But I may not constrain you whether it's just one side. I don't really care. It will be front and back of that one page of notes. That's probably what it will be. If it's something else, I'll let you know on Thursday, and I'll try to verify that as far as what I want to have happen on Thursday for a week from today. Other questions on what has happened or what is scheduled to happen? Let's get on with talking about these equivalents. I'll try to write down the idea behind these. I think it was good that some of you actually said you tried to read it in the book and it wasn't making a lot of sense. And so hopefully it will make more sense with today's class. But the idea is to replace a complex circuit between 2 nodes. So you've now identified 2 nodes that you want to examine the behavior relative to those 2 nodes. You may want to hang something onto those 2 nodes, a load or something else, some other circuit. You want to know, what does that look like? What's that complex network look like relative to those 2 nodes? And we'll probably label those A and B. So we want to replace that complex circuit between 2 nodes with a simple source network. And that source could be either a voltage source or it could be a current source. And it's not just a source, it's also with a particular resistance. The voltage source, it's going to be in series with a resistor. So I'll say a voltage source with a series resistor, or series R, or if we have a current source, that will be together or combined with a resistor in parallel with the current source. That's the structure that we will assume our simple source network possesses or looks like. What we want to do is preserve the behavior of that complex circuit with the simple circuit at the two terminals. We're not saying that what happens internal or beyond or in that black box is going to be the same. We're just saying relative to those two terminals, we're going to see the same behavior if we hang something on those, if we replace that complex circuit with something simpler. Here's what's happening with a picture. Or pictorially. We might have some mess, which I will just say a complex network. Coming out of that complex network, we've actually identified two nodes or two terminals, and we'll call those A and B. We're going to replace that complex circuitry in that blue box with something easier. It'll make our analysis easier. And what we're going to do is that black box is going to become one of two things. If we wanted a Thevenin equivalent, then what's in that blue box is going to be this simpler circuit with a voltage V sub t and a resistor R sub t, where the t is for Thevenin. We have a Thevenin resistance and a Thevenin voltage source. These terminals A and B are the same. That's the Thevenin equivalent. We want to boil everything down or collapse everything in the complex network. If that's just a box and somebody pulls out two terminals, they say, okay, model this device, whatever's in there, with a source and a resistor. In this case, in the Thevenin equivalent, it's a voltage source in series with a resistor. If somebody says, you know what, I don't want my source to have or be represented by a voltage source, I would prefer to have a current source. If that's the case, then this is another equivalent simpler circuit, which is called a Norton equivalent. And its terminal behavior between terminals A and B should be the same as that complex network's behavior between terminals A and B. It's just now we are thinking about replacing that complex network now with a current source, and that current source is in parallel with a resistor, and it's not just a function of me being careless, but that R sub t is the same value in both networks. If indeed you do have, if you have identified that series resistor in the Thevenin equivalent, it's not too difficult to actually say, oh gosh, I wanted a Norton equivalent, to derive the Norton equivalent. You can just replace the voltage source with a current source. The resistor maintains the same value, but now it's going to be in parallel instead of in series. That should be all you need. No, that's the process to read on your own is page 90. Let's try to work through some examples, or at least one. Here's one such example. It may not seem that complex, but at least hopefully you will start to get the idea of what's going on. Suppose that somebody says, okay, here's your complex circuit. It's made up of 3 resistors and a voltage source. Here are your terminals A and B. And I want you to collapse that down into a simpler circuit with just a series combination of a voltage source and a resistor. So we're wanting this. Or maybe not look like, that's maybe a poor choice of words. We want, let me just say, we want a Thevenin equivalent, which means that our circuit that we want looks like that. And in order for that to be equivalent between terminals A and B, if I took an ohm meter and I simply set it between points A and B, if I connected the positive lead to A and the negative lead to B, what's the voltage I would measure? Those 2 terminals are open circuited. They are not connected together, they're separated, so that's called an open circuit. And I could say, well, that's my open circuit voltage. I could measure that voltage. If the top complex network is supposed to be equivalent at terminals A and B, then I should measure the same voltage, open circuit voltage, in the bottom, Thevenin equivalent, as what I would measure in the top complex circuit. For equivalence, V sub open circuit, or the open circuit voltage, must be the same in both circuits. If that's the case, let's just do a little analysis on this Thevenin equivalent. This is the Thevenin equivalent. Why don't I just, as a way of practicing for the exam, I could write a KVL relative to that Thevenin equivalent. Meaning I could call that some current I, and then I have my voltage source and this resistor. If I write KVL in terms of those variables, I have starting down here at the lower left, I have minus V sub t, I'm going in the negative terminal. I have plus R sub t I plus V sub OC. The OC, was that a TV show? That's not where we're at, but you're seeing that particular voltage drop, equal to 0. What can you tell me about I? Does it even exist? If that's open, circuited, if there's no connection between A and B, how much current can flow out of A or into B? 0. So I, in this case, is actually not even there, which says that V sub t is V open circuit, which, if we wanted to find a Thevenin equivalent, all we would have to do is get a voltmeter, measure the voltage dropped across AB in that open circuit configuration, and say, oh, that's my source voltage in my Thevenin equivalent. That's V open circuit. I can do this experimentally. Obviously, in this class, we're not going to do it experimentally. You're going to find that V open circuit with analysis. But if we can find V open circuit in the original circuit, we can set that measured or that determined open circuit voltage, we can set it equal to our Thevenin source voltage V sub t. Questions on that? If that Thevenin equivalent needs to be equivalent to the complex network, they should have the same voltage across the two terminals, if they're equivalent at the terminals. They also need to be equivalent in another way. Suppose that I put an ammeter between A and B, and I say, you know what? I want to basically short out terminals A and B with my ammeter and measure the current that's flowing. That's going to be called the short circuit current. They both should have the same short circuit current. If I put a device that measures current flow, and that's effectively shorting points A and B together, and I'm just measuring the current flowing through those, then those two networks should give me the same short circuit current. What I'm trying to say then is also, for equivalence, the short circuit current in both networks must be the same. Let's look at what that looks like in the Thevenin equivalent. I was just waving my hands. Maybe it wasn't clear what I was doing. Here's what I was trying to suggest was happening. I'm calling this V sub t and R sub t. Here are my two terminals, A and B. What I want to do is actually connect those two terminals with a wire and then measure or calculate with analysis what that current is going to be when it flows through that circuit. Now it will allow for a current to flow. That circuit path is connected. It's complete. There can be a current flowing, and that's what we will call the short circuit current, because we're short-circuiting nodes A and B together. We're just effectively connecting those. What if we now write a KVL equation for this scenario? We now have minus V sub t plus R sub t I sub short circuit equal 0. Or we now can say that our Thevenin voltage, which we may have already measured, must be proportional to the short circuit current, and that proportionality constant is actually that Thevenin resistor R sub t. Simply by doing some algebra on that KVL equation, or moving V sub t to the other side, one side or the other. Or if you were actually doing this experimentally and you had your voltmeter and you connected it across A and B and you measured the voltage, that's V Thevenin. Then you reconnect your multimeter to where it's an ammeter and you connect nodes A and B and you read how much current is flowing. Now you've measured your short circuit current. Now you have those two quantities determined. If you have those two quantities determined, I was going to point at my tablet, and that would really be effective. You've now measured this, and you've measured that. There's only one unknown in that equation, and you can solve for it. Meaning you can now say, oh, if I know my short circuit current and my Thevenin open circuit voltage, I can now compute my Thevenin resistance, R sub T. It's the ratio of that open circuit voltage to the short circuit current. So if you did, I'm sorry?
The way we would know the short circuit current would be given because we're assuming that you took an ammeter and measured it for us?
Yes, so, well, that's if the question was, how would we know what I sub short circuit actually is? And you can do it many different ways, but what I was just trying to get you to think about was to do it experimentally. If you could physically go in the lab and somebody gave you this box and they said, oh, here are your two terminals, tell me what it's equivalent to, or give me its Thevenin equivalence. You could now connect those two leads to your ohm meter and measure V open circuit, and you could reconnect your multimeter to where it's now an ammeter, and it's effectively shorting node A and B together, but measuring the current that's flowing through that short. You now have measured V sub T and I sub short circuit. If you have those two measured, you can now compute your Thevenin resistance. If you can't go in the lab, or if you don't have that, if I now give you a circuit, you would have to analyze that circuit to determine your open circuit voltage and your short circuit current in those two different configurations. Obviously, you're looking at two different circuits, but I mean two different configurations of the same circuit. But once you've computed the open circuit voltage and the short circuit current, you can now compute your Thevenin resistance. Does that answer your question? If we can find the short circuit current in the original circuit, then we can determine the Thevenin resistance R sub T in the Thevenin equivalent circuit by using those two quantities that we've just determined, by using V sub T and I short circuit. Let's see if we can do that for our example as an illustration. Here was our circuit, our complex circuit. How do we want to analyze that? What I want to do is find this voltage, VOC minus. How would you analyze that? Given all of your skills that you've now learned so far this semester, how would you analyze or compute V sub OC, or the voltage drop across nodes A and B? Okay, can you short it out and then find the current through that? Would that give you VOC? Eventually. Actually, you would be changing the configuration if you shorted it out. If you shorted it out, you're getting to the next step, and we would find I short circuit if you shorted out A and B, and that would give you half of your answer. Okay, so now do we want to try to find the equivalent resistance between resistors 6 and 7? Not for finding the open circuit. We don't really want to change anything. We just want to determine or calculate what that voltage drop across AB is. Yes? Since they're in parallel, is it just 12 volts? Is VOC actually in parallel with the 12-volt source? Is that what you're asking? Is it? Now, what is actually happening? So the short answer is it's not quite, because you have 12 volts actually dropped across this guy and that guy, don't you? And we just want the drop across that one. So you could do mesh, you could do a voltage divider, you could do all sorts of things, can't you? You simply want to know how much of that 12-volt source voltage is dropped across that 6 ohm resistor. How much current is flowing here? How much is flowing left or right across that 7 ohm resistor? 0. It's opened up. Nothing's going there. That's a good thing in terms of computing VOC. That means you can basically neglect that 7 ohm resistor, can't you? If you virtually get rid of that, if you just say, you know what, that's no longer there, my A is actually right there in a sense. Now maybe you can more easily see that voltage divider that I was referring to before. You now have 12 volts from there to there, and you want to now see what is my open circuit voltage. Maybe that doesn't make any sense to you. You can do a KVL. You could say, you know what, I hadn't a clue what he was talking about, but I know how to do my KVL equations. That's okay also. You could write a KVL equation. Let's say this was I. What is KVL now in that mesh? It's minus 12 plus 3I plus 6I equaling 0. Yes or no? Is that okay? Is that one easier to see?
How do we find I?
How do we find I? How many unknowns do we have in that equation? 1. Luckily we found it, haven't we? So, yes, now we have I because we have one equation in the one unknown. So that's what we were wanting. But once we have I, we don't have our complete answer, do we? This is an intermediate variable. We wanted I, this approach, so that we could compute VOC. But let's just find I for now, if I can. So now we have 9I is equal to 12, if I'm doing the algebra correctly. Or I is now 12 over 9, or 4/3 of an amp. Are we done? No. We have an intermediate number or variable, but that's not the answer, is it? We want VOC. What is VOC? Okay, you way ahead of me. Before we get to 8, what is it? It's Ohm's law, correct? It's R times I. R is 6, and I, we just computed. You're taking out all my fun, because I kind of like to cross things out. And now we have 8 volts. That's VOC. We could have found that via the voltage divider.
Will there be problems where we have to solve like a different way, or
Will there be problems where we have to solve it a different way? Maybe. I would suggest that you maybe get really comfortable with 1 or 2 techniques, and maybe you can use that all the time. But I'm just trying to show you different ways that you could get the same material or information, and one way might click with somebody, another way might work for another student. And the idea is it doesn't really matter how you solve it as long as you do it correctly.
So generally, we will be able to use KVL.
So generally, you can probably do KVL. You could maybe do nodal, but as we've learned, one might be easier than the other for a given situation or a given circuit. If I wanted to find, well, what if I wanted to use a voltage divider expression to find the VOC? VOC, what's my total resistance that 12-volt source sees? Does it see the 7? No, because there's no current flowing. There's nothing that's basically infinite relative to the 12-volt source, because it's not connected. What the 12-volt source sees, total impedance or total resistance, is the series combination of 3 and 6. Right? So that's what's going to be in my denominator of my of my voltage divider expression. That's 3 plus 6. What's going to be in the numerator? And this is going to be multiplied by my total voltage, 12. And which resistor, scroll here. You'll scroll here in a minute. Sorry, I'm talking to myself. You didn't see what I was seeing, maybe if you were frantically. We're trying to get the drop across the 6, and that's what's in our numerator. So that now we have 6 over 9 times 12, and we better be getting the same answer that we had before. Here's my 9, which I can say goes in there 4 times. Now I have 24 over 3, which is just another way of writing 8. And maybe that approach seems easier to you, but it's going to depend on your circuit, how complex your circuit is. This one's not too complicated.
Can you write out symbolically what you did for voltage divider?
So what did I write out, or what did I just do for my voltage divider? VOC is sort of like R2 over R1 plus R2 over V total. Is that what you meant as far as my voltage divider expression? Or if I had more resistors, then I would have to include all of those in the bottom denominator, and I would just be isolating on the one resistor that I'm interested in the voltage drop across. Other questions? I'm halfway there. I found my open circuit voltage, which is my Thevenin voltage, V sub t. I want to now get my next piece, which is my short circuit current. Now I can short terminals A and B. Now I want to reconfigure my system, and I would just redraw it so that it's easier to see. I wouldn't try to do too much of this in my head. It's not worth it. Here's 3, here's 6, here's 7. Here is A and B. And now what I'm doing is I'm shorting those out. And you guys probably want to do this that way. Yes or no? Maybe. Let's do it this way. We'll do it another way, and then we'll see what you like. What is I short circuit? It's this current right here. But in terms of I1 and I2, what is I short circuit? Is everybody okay with that? I sub 2 is I short circuit. If I can compute or find I sub 2, I found I short circuit. How many equations am I looking to find now? 2, because I have 2 unknowns. I sub 1. I need to get better with my pen. I have two equations with the two unknowns, I sub 1 and I sub 2. KVL around mesh 1. If I start down here, I'm now going through the negative terminal, or entering the negative terminal of my source first. That's now minus 12 plus 3 times I1 plus 6 times what? I1 minus I2. The net current going down in this mesh is I1 minus I2 equals 0. How about KVL on mesh 2? Now if I start here and go clockwise, I have 6 times what current now? Now I want my drop to be positive from bottom to top. So now this one is going to be 6 times I sub 2 minus I sub 1. Is everybody okay with that? And then I have plus 7 times I sub 2 equaling 0. There are my two equations in two unknowns, and I can now solve for, I need I sub 2. If I just rewrite those, and some people have been getting really nervous when I guess my solutions might be in matrix form. How many people are uncomfortable with matrices? I'm sorry, that's a bad question to ask in front of your colleagues or peers, so you could sit on your hands, it doesn't matter. But maybe you're not comfortable with matrices. I'll try to put those down occasionally so that you'll start to feel warm and fuzzy with matrices. Question?
Because we found for this VOC, we wouldn't add equals to that second.
Oh, so now that we've found VOC, I'm rephrasing your question, do we use it in this analysis? And the answer is no. We're going to use it later after we've done this analysis to find I short circuit. So we need to look at the circuit in two different situations. In the first case, to find VOC. In the second case, we're shorting out A and B, and we just want to find I short circuit. Once we found I short circuit and VOC, then we can combine those two pieces of information to get everything we need, which is either the open circuit voltage, which is V Thevenin, and our Thevenin resistance, R sub T, or we could say, oh, what's my Norton current source and my Thevenin resistor or Norton resistor, R sub T. In this case, I can collect my terms, and I should have, maybe you're more comfortable saying, oh, that's 9I1 minus 6I sub 2 is equal to 12. That's from the first equation. The second equation is minus 6I1 plus 13I sub 2 is equal to 0. I'm saying that if you wrote that in matrix form, you would write it in that way. Is that okay? And now if you have your expensive calculator that you convinced mom and dad to buy you, you can compute I1 and I2, or you can use Kramer's rule. You can do whatever you want to try to find I1 and I2. Or if you want to do it old school, you could say, you know what, I can find I1 in terms of I2 from that bottom equation. There's nothing on the right. And I can say now that I1 is equal to 13 over 6 I sub 2. Did I do that right? And once I have that, I can plug that in here in the first equation, and now I have 9 times I1, which is 13 over 6 I sub 2 minus 6 I sub 2 is equal to 12. Or I now have 39 over 2 I sub 2 minus 6 I sub 2 equaling 12. Or I sub 2 is now 27 over 2 and it's a good thing I remembered my multiplication tables. 3 goes into both of those, correct? And I now have I sub 2 is 8/9 if I've done the algebra correctly. What's my, that is I short circuit. In another circuit in your analysis, I short circuit might end up being I sub 7. Or it might be I sub 7 minus I sub 2 or something. But in this case, it was equivalent to I sub 2. And now we're almost finished. We can say, oh, my RT is VT over I short circuit. And what was VT? Was that 8?
Yeah.
And I short circuit was 8 over 9. Oh, this is fun. So that's 9 ohms. And now we have our Thevenin equivalent. We could say, oh, here's my source voltage, VT, is 8 volts. Here's my Thevenin resistance. And that circuit looks the same from terminals A, B as my more complicated circuit that I started with.
Does that just mean at the terminals it acts the same way?
Yes, that only means that at the terminals it acts the same way. What's going on inside may be completely different in your box. Now we've replaced our blue box with that equivalent circuit that will, at the terminals, behave the same way. Meaning if I now, and why would this maybe be useful? Well, if you are now connecting many different things to these terminals A, B, now you can maybe easily compute what the behavior would be if you put many different resistors on that AB, those AB nodes, or between those two nodes. That might be beneficial to you. Questions on that? Yes?
Are we going to be finding the resistance by getting rid of the source?
So can we get rid, do you want me, so the question was, are we going to find the equivalent resistance by eliminating the sources? And yes, we can. That's another way to find the equivalent resistance. But you can only get rid of the independent sources. You have to keep your dependent sources active. You can't kill those. You can kill your independent sources. What does that mean? That means set them equal to 0 and see what happens when you look back into terminals A, B. Before we do that, suppose that I find, so we found V open circuit 2 ways, didn't we? We did a KVL and we did a voltage divider. We found I short circuit 1 way using a couple of KVLs. Why don't we find I short circuit another way? We found in the first analysis I short circuit using KVL or mesh. Why could we do it with nodal? Here's our circuit. Can I analyze this circuit using nodal analysis? Is it even allowed? Where are my nodes? Or do I even have a node? What am I trying to find? I would really like to find this, wouldn't I? I would really like to find I short circuit. But you know, the nice thing about the first part of school, you still have plenty of paper, your pencils are probably still sharp, and you maybe even convinced your mom and dad to buy you some colored pencils so you could write with different colors. So you say, you know what, I want to redraw this. It doesn't look quite right to me. So you say, you know what, I'm going to do it in green. Now does it look better for writing KVL? Yes, no. Really, I haven't changed anything. I've just shortened AB and lengthened that wire connecting 6 and 7 a little bit. But what I've tried to do was identify that here is my node that I want to concentrate on, and let me call that V sub 1. Or what I'm saying is here is V1. My reference node is the bottom node shared by the 12-volt source, the 6 and 7 ohm resistor. Where's I short circuit? Is it gone? Have I eliminated it? I short circuit initially was right here. But that's exactly the same current as what's flowing from left to right in 7, which is exactly the same as this current flowing down. Does everybody see that in that redrawn circuit? In the redrawn circuit, if I now compute or calculate KCL, I'm going to say, you know what, I want to find that current, I want that current, and I want that current. All three currents are leaving that node. I'm going to say all three of those must sum to equal 0 by KCL. If that's the case, what's the current going from right to left through the 3 ohm resistor? What's an expression for that? Is everybody okay with that formula? My voltage now I want to be positive, let's say, from V1 to 12, because that's the direction that I've identified that current going in that I want to express as an expression. And that expression now needs to be V1 minus 12. That gives me the voltage drop across that resistor. The current flowing through that resistor in that direction needs to be divided by the resistor, which is 3. What's the current going vertically down? V1 over 6. What's the current going to the right? Where's my second equation? When I did KVLs, I had 2 currents. Do I need a second equation? I'm going to fall down going backwards up the stairs. That'd be funny, wouldn't it? Hey, guess what happened in class today? The instructor fell down. Pretty fun. How many equations am I looking for now with nodal analysis? 1. So now maybe this was easier. Maybe it was easier to do nodal analysis, but if you didn't see it right off, it doesn't matter. That's okay. It didn't take you too long to do 2 equations and 2 unknowns, but now we have 1 equation and the 1 unknown, and once I find that 1 unknown, V sub 1, I can compute I short circuit. You just told me that's going to be, what is I short circuit going to be if I find V1? If I know V1, V1 over 7 is going to be I short circuit. So let's compute V1. V1 is 1/3 plus 1/6 plus 1/7 times V1 is equal to 12 over 3, but that's just 4. Or 42 makes a nice denominator for those three, and I now have, is it 14? 3 14s give me 42. 7 6s and 6 7s. Now I have V1 is equal to 4 times 42 divided by 27. Is that right? And what do I know? Anything? Don't answer that. You don't have to laugh either. 3 goes into those two. 9 times here and 14 there. So I now have 56 over 9. That looks really nice. But I need I short circuit. That's V1 over 7. Now it's looking better. So I have 56 over 9 all over 7. This, is that what we had before? Yay! That's what we wanted. And now you can get R Thevenin if you wanted to. Questions on that? We obtained V open circuit 2 different ways. We didn't have to do it 2 ways. We obtained I short circuit 2 different ways. All we needed was 1. You figure out which one seems to work for you. It doesn't really matter. Let's now go on and see what was an earlier question. We could actually find our Thevenin resistance in some cases by zeroing out our sources. So what we want to do is zero the independent, and it's critical that you don't zero out your dependent sources. You can only zero the independent sources. Zero the independent sources. And find R sub t, or R equivalent, between nodes A and B. Let's do that with our example circuit, our complex circuit. That circuit looked like that. We want to turn all the independent sources off and measure with analysis, essentially, determine what is the resistance seen across or between terminals A and B. What's going to happen if we zero this source? What do we do with voltage sources, independent voltage sources, if we zero them out? What does that mean? A wire. We short them out. We replace that with a wire. We can now redraw this and say, you know what, if I'm zeroing out that source, this is now what my circuit looks like. Here's a 3, here's a 6, and here's a 7. Questions on that? I now want to find the equivalent resistance between nodes A and B, or terminals A and B. Can I simplify that at all? Pardon? 3 and 6 are in parallel. They don't look like they're in parallel. They look like they're kind of perpendicular to each other. But we can stretch and shrink wire, can't we? If it doesn't look parallel to you, then get out your colored pencils and redraw it. And just say, you know what, it doesn't really matter. I can stretch these wires. Here's A, B, here's 7, here's 6, and there's 3. And what I want to do is replace those with their equivalent parallel combination. They are in parallel. Let me call that R1. Oh, I was going to say bar, but somebody doesn't like bars in here, do they? How about tilde? So an R sub 1 tilde. What's the equation for that?
1 over 3 plus 1 over 6 is 1 over the whole thing.
Okay, the inverse of 1 over 3 plus 1 over 6. Or I remember it this way for just 2. It's their product over their sum. And that now says it's 18 over 9, or 2. If you're doing it with a calculator, probably the inverse thing is going to be fairly quick to do. But now, if I'm doing it on paper and pencil, if the numbers look nice, then I'll do it this way. And 2 seems to make sense because my equivalent resistance should be bigger or less than any of the ones that I'm combining in parallel. Less. And that's less than 3 and less than 6. So that makes me feel okay. Now I have a circuit between A and B. There's 7, and now I can replace those 2 that were in parallel with 2. And what's my resistance between A and B, which is my R sub T in this case? 9, and that better be the same as what we computed before. Is that true? So that's another way to find the Thevenin resistance, is to zero your independent sources and combine the resistors in a way that you can easily determine what the total resistance or the equivalent resistance is between nodes A and B. Questions? That's Thevenin. What about Norton? Don't want to shortchange Norton, although we are going to. But once you have the Thevenin equivalent, it's not too hard to find the Norton equivalent. And these two should be equivalent relative to terminals A and B. Here's VT, RT. If those have the same terminal characteristics or behavior, what is this? Those should be the same. What is VOC in the Norton? Or that's V between A and B. In the Norton equivalent, oh well, in the Thevenin equivalent, that's just V sub T, right? There's no current flowing. And so VOC is the same as VT, since the voltage drop across R sub T is nothing. Does everybody see that? But that should be the same as VOC in the Norton. And what is VOC in the Norton? That IN is only going one place, and it's only circulating around R sub T, correct? And that current I sub T flowing through that current I sub N flowing through R sub T establishes a voltage drop across AB, and that voltage drop is plus to minus VOC. Because that current I sub N is coming in the positive terminal of R sub T, the way that we've labeled VOC. So that if we wanted this current source, I sub N, we could find it once we found the Thevenin voltage and the Thevenin resistance. We can find, based on this equation, we can now find I sub N. And now we have the ability to find either the Norton equivalent or the Thevenin equivalent. So that another way of thinking of that is, what is I Norton? If we are shorting A and B, what happens if we short AB in the Norton equivalent? Where does that I sub N, where does that current source go? It's a current divider, isn't it? If I put a wire between A and B and the Norton equivalent, how much of I sub N is going to go through that wire? All of it. Resistance, or current seeks the path of least resistance. If I disappear in that, I guess you can go home, right? If I disappear down these floors. I'm kind of curious, but I maybe have to wait until you guys leave, and then I'll lift up the floor and see what's under there. Where were we? All of it. All of it. Thank you. All of it. All of the current goes through that short. What is the short circuit current in my Thevenin? So what we just said is I short circuit is I sub N. In the Thevenin circuit, if I short that, what's my expression for my current, I short circuit? On the Thevenin side, if I gave that to you on an exam, when you hand in your exam, you should say thank you. It's VT over R sub T, correct? I short circuit in the Thevenin equivalent, meaning now that's V sub T over R sub T. We found this from the Norton and this from the Thevenin. Questions on that? Now we know how to go back and forth between a Thevenin and a Norton. Or we can now say, oh, you know what? We know how to make these two source combinations of a current source and a resistor equivalent to a voltage source and a resistor. We know the relationship, which means if I wanted to simplify a circuit, I could do that via source transformations. I know you're going to get sick of this circuit, but just enjoy. Here's AB. Here's 12 volts, 3, 6, and 7. What do I mean? Well, let's say that I start doing source transformations to try to get a Thevenin equivalent between nodes A and B. So now I'm going to start at the left and try to progress to the right and end up with just a voltage source in series with a resistor, which means initially I can't really do anything unless I could replace this with a resistor in parallel and a current source. Then I could combine that. So what I'm doing, or trying to talk my way through, is let me isolate on those two and try to replace that. I'm now trying to get rid of this or rewrite that in terms of an equivalent source. What is this and what is this resistance? If this is my Norton source equivalent or Norton equivalent and here's my Thevenin equivalent, what did I know about the resistor in those two equivalents? It's the same. So do I now know that that's 3? What is my current source value? Now I just need to go back up top a little ways and say, oh, my relationship between my source current and my voltage source, Thevenin resistor, is just I take the ratio, V over R. I had 12 volts and I had 3 ohms. So this is now 12 over 3, or 4. I've now replaced that voltage source in series with a resistor with a parallel combination of a resistor and a current source, where the current source is 4 amps and my resistor is 3. Now the reason I did that is so that I can now combine those two resistors. They're in parallel. Let me now make that simplification. Now I can say that I have this and what is this guy? That's 2, isn't it? That's that R sub 1 tilde from before. That was 3 in parallel with 6, which was 3 times 6 over 3 plus 6, which is 2. Well,
Can you look back up to the other diagram?
that one?
Yeah.
Is everybody okay with what I'm doing? I'm now trying to go from left to right, and I'm trying to collapse my complex circuit by doing source transformations and work my way back to terminals A, B, so that eventually I only end up with one resistor in series with one voltage source. The very first step was to transform my voltage source in series with my resistor into a Norton equivalent. That allowed me now to put that 3 in parallel with 6, which collapses down to 2 ohms. Now what I want to do, I'm sorry, I switched back, is that okay? Or I scrolled down. Now what do I do? Now I look at these terminals to the left and say, I can't combine that 2 with the 7. I could if it was in series. Let me now do a Thevenin equivalent on this piece right here. Meaning, now I want to make that look like the following. What's this resistor? That has to be the same, doesn't it? What is this? Maybe I should call this something else. That's V sub T Thevenin. Actually, it's going to be my V Thevenin, so maybe I can just call it VT now. What is it? It's my I sub N in my Norton equivalent times my R sub T in that case, which is 2, which is and now I have these two in series, so that I've now found my Thevenin equivalent by doing source transformations. There's 9 and here's 8 volts. And that's now the same between terminals A and B. I just found it a different way. Questions on that? I'm sorry? So now how did I get, I'm not sure how far back you want me to go, but here, maybe in this, what am I doing? I'm now replacing this Norton equivalent right here with a Thevenin equivalent. And if I replace one source with the other, what happens to my resistor? It's the same, isn't it? So this 2 ohm resistor in series with some source, I have to figure out what that source is, but I know that that 2 ohm resistor is going to be the same as my parallel resistor in the Norton source. Does that help answer your question?
So in this one, you're disregarding the 7 as well?
So in this one right here, I'm not yet far enough. The question was, are you disregarding 7? I'm not really disregarding it. I just don't worry about it until I get there. And I haven't yet gotten to the 7 yet until I now have this series combination of resistors. Now I can combine that 2 and 7 into one resistor, which is 9. Questions on that? Why is everybody so anxious? We still have another topic to go. We still have 40 minutes. Any questions on this? Let's talk quickly about the Wheatstone bridge. This one's easier, I think, for you to understand. And I'm going to do it all in highlight, so actually, I just like drawing this picture. Let me try to explain what's going on. We have this interesting combination of resistors, and here is actually a meter that will measure current flowing between 2 nodes, let's say A and B, and here's R1, here's R sub 2, here's an unknown resistor, which might be a strain gauge on a bridge. There's R sub 3, and now we're going to energize that combination of resistors with a DC voltage source. This is unknown.
What's in the center?
What's in the center? A circle with an arrow in it, which is a meter that's going to measure current flowing from A to B. It's a deflection meter. If there's current flowing, it's going to show. The idea is we want that needle to, we are actually going to adjust this resistor and that resistor. Those are pretty bad looking resistors, but you can clean yours up. We want to adjust R sub 2 and R sub 3. Those are under our control. We can adjust R sub 2 and R sub 3. The reason we want to tweak R sub 2 and R sub 3 is to try to make that needle go to 0, to not have any current flowing between A and B. If I do not have any current flowing in A and B, what do I know about this current, that current, and this current? What do I know about the relationship? Let me call this I sub 1. Let me call this I sub 3. And let me call this I sub G. If there's no current flowing between A and B, what do I know about I1 and I3? They're equal. Is everybody okay with that? You can do the same thing on this side. You could say, well, here's a current I sub 2. Here's a current I sub 4, or I sub x. I sub g is still 0. What do you know about B? A KCL at B. You now know I2 is the same as I4. What if you were to do a KVL around any of these paths? Let me say that this, well, how do they do it in the book? Let me call this plus VAB minus. What if I did a KVL around the top? Meaning, what if I went, oh, I don't know which direction I want to go. Let me go this way. KVL around there. What would happen? I would say plus R sub 2, I sub 2 for that drop across that resistor. Now if I want to go from B to A, it's minus V sub AB plus, actually it's not plus because I'm going against the arrow now, and so now I have minus R sub 1, I sub 1 equaling 0. If there's no current flowing through that needle or that meter, what do I know about VAB? It's 0. Now you have a relationship between I1, I2, R1, and R2. You can use that information, read the book, I think it'll be clear, and you'll end up with a formula for R sub x. R sub x will end up being R sub 2 over R1 times R sub 3. You'll be able to tell what R sub 2, R sub 3, and R sub 1 are by your adjustment. You'll be able to solve for this unknown R sub x. We'll probably start with chapter 3 on Thursday.